Hello students, and welcome to section 2.5 part B, continuation of yesterday's discussion from 2.5. Solving inequalities and equations algebraically and graphically. To start with today, we're going to take a look at something called the boundary algorithm. We're going to solve a boundary equation, determine test intervals. Plotting test points may help. Pick a test point per interval and test intervals, and include intervals that make the inequality true in the solution. As we take a look at this very first example, it says find the implied domain of each expression. So for number one, we have the square root of x squared minus 4. Now we should recall that x squared minus 4 is a quadratic that we can actually solve separately on its own. However, in this particular case, because it's under a square root, we're going to need to set it greater than or equal to 0. The reason we set it greater than or equal to 0 again is we cannot take the square root of a negative number. We can take the square root of 0. We can also take the square root of a number that's positive. We cannot take the square root of a negative. So a positive boundary is what we're looking for. So I took this radicand, as you can see, and I set it greater than or equal to 0. We can actually factor this accordingly, so x plus 2 and x minus 2, and I rewrote it as equals 0. The reason I rewrote it as equals 0 is because I'm going to be solving for two critical numbers, we say. The first critical number is negative 2 when you set it equal to 0. You want to plot that on the number line, and also positive 2. Okay, so how do I know where to graph? Am I going to be graphing to the left of negative 2, to the right of negative 2, left of positive 2, right of positive 2? As it turns out, well, two things actually apply when I look at this original inequality. The first of which I've already denoted as a positive value. I've also noted here closed. Now the closed speaks to greater than or equal to. Okay, so we have two closed circles at those two critical values, we say. But what we're going to want to do to determine if we're going to shade to the left or to the right of that point, or left or right of that point, is we're going to pick some test points. It's actually very straightforward to just jump on the calculator and do an analysis of quite literally plugging in a number that's less than the first critical number, negative 2. And when I type in, as I store here, of course, negative 3, for example, but I type in the quadratic x squared minus 4. You could do this without a calculator, of course, but it turns out that that number ends up being a positive number. Because it's a positive number, this is very quick and easy to see, therefore, that you're going to graph to the left of negative 2. You could test a number like 0, but that's pretty quick to see. If you plug in 0 here, I'll just show you without a calculator. 0 squared minus 4, that's negative 4, which is not greater than or equal to 0. So you don't graph in between. Picking a number like 3 should also yield a positive result. If you just pick 3, of course, we can store it as x. And then hit enter, and then second enter again. And that's going to give us, again, the quadratic, and get, of course, a positive output. This positive value, again, dictates us shading to the right of 2. The final answer ends up being this, negative infinity to negative 2 with a bracket, and then bracket 2 to infinity, and you're in union with these two intervals. I'm going to leave example 2 for you to take a look at on your own, though please note it's a positive and closed interval again because of the inequality. Please take a look at that on your own. Solve it in a very similar manner. The properties or inequalities to follow here, as you can see, let A, B, and C, and D for that matter, be real numbers. The transitive property applies, the addition of inequalities, the addition of a constant, but also the multiplication by a constant. So please take a look at those. When we verify solutions graphically, it is a great way to check your answers. Method 1 is to rewrite it in the form of y equals 0, with 0 on one side and all non-zero terms on the other. Choose an appropriate view window and graph the quadratic, or equation for that matter. Could be any function. Maybe I'll use the last example to highlight this in a moment. Use the 0 feature to approximate the x-intercepts. And then method 2 is to graph the right side, graph the left side, y1, y2 there. Use the intersect feature, and then from there the x value of the intersection will correspond to the solution or solutions. I do want to maybe take a quick moment just to highlight how number 1, using method let's just say 1, will be nicely applicable. So how about we graph y equals the square root of x squared minus 4. Okay, so y equals, let's clear those, the square root of x squared minus 4. This will not look like something that we've quite yet seen. However, it is something that we can justify using the same analysis that we did on the number line. As a matter of fact, if you look at the graph, -2, remember, was a critical number, if you recall. There it is, as was +2. Now remember, because we want, if we look at this inequality again, because we want values that are greater than or equal to 0, we want the function, albeit a square root of a quadratic, to be greater than or equal to 0, in other words, above the x-axis. So where is this curve above the x-axis? Well, it's above between -infinity to -2. Where else is it above the x-axis? +2 to infinity. So again, -infinity to -2 above, and +2 off to infinity above the x-axis. So that's a quick way to look at the graph and make a quick assessment as to how the inequalities are going to frame out, but also how the number line in turn, as you see the interval notation, frame up or frame out. Let's take a look at the next page. I wanted to show you how the graph will take shape. So we may use some graphs down the road. Let's just take a look. Solving various types of equations. Solve each equation algebraically and verify your solution graphically. So quadratic form equations, we're going to solve this. Now we have used U substitution in the past. I want to make it very clear that you don't have to use U substitution, although I think it does help. So U in this particular case is going to be x squared. And if that's the case, if you square both sides, you get this, u squared equals x to the 4th. So then this becomes u squared, this becomes minus 6u, and this is still just plus 5 equals 0. This is a nice version of a quadratic that we can quickly and easily factor and then solve. As you can see, two numbers that multiply to multiply to positive 5 and add to -6 are -1 and -5. So there's your factored form using u. We still got to set it up though with x. So x squared minus 1, again, here's what u was, right? X squared minus 1, and then here x squared minus 5. Set it equal to 0. We'll set this individually equal to 0. We'll get x squared equals 1, and solving we'll get plus or minus 1. Here, same type of thing, add 5 after setting it equal to 0, square root both sides, and plus or minus root 5. In terms of the graphing version, or I guess aspect of this, you could graph. I will ask that you verify that separately. This is a good example of something that you are solving without necessarily using any inequalities technically. Later we will again be using inequalities. I will ask that you go ahead and try the next example here on your own. Just as a quick comment though, and this will be something we don't need to do. I'll delete that. We're going to ask on some of these to do some different graphing techniques. By grouping is the approach that you're going to utilize here. So if you recall from Algebra 1 and Algebra 2, factor by grouping entails parentheses and then parentheses again, but notice the change in the signs here. I turn this from a minus to a plus and negative, and the negative goes inside the parentheses here. Please go ahead and try that problem on your own, and hopefully you'll end up getting those respective zeros. The last problem on this page I will also ask that you try on your own. This particular question is one where you'll need to get the square root isolated, and you can do that by adding 3x to both sides. And look, the square root is isolated. All you got to do is square both sides and take it from there. You'll end up with one answer that works and one answer that doesn't, but please take a look at that. On the next page, another problem to solve. In this particular case, I'll dig a little bit deeper with you on this. If you go ahead and try to get the square roots by themselves, see if I can delete that, you can actually do so by subtracting root x. The problem is on the right side, you still got an interesting looking binomial, 10 minus root x. Nonetheless, you'll still square both sides and go from there. When you square both sides, here's the left side simplified, the right side foiled, because you'll have to FOIL this binomial. You can in turn subtract x from both sides, balance your equation. In the next step, you'll still have a square root to deal with if you divide both sides by -20, but that's actually not so bad if you square both sides and solve. X equals 36 will be your result. Please take a look at the next example on your own as you solve this. You will have to raise both sides of the equation to the reciprocal power here. In other words, if 4/3 is the exponent, raising both sides to the 3/4 power will undo that particular operation. Please take a look at this. It entails splitting the problem up into two separate cases, so to speak, because the 4th root of this number 16 to the 3rd, the 4th root of 16 to the 3rd ends up being 8. Okay, but technically speaking, remember when you take an even root of something, you have to include plus or minus. So this problem has a positive version that you're equating the quadratic to, and also a negative version. This is actually fairly nice to solve. This one, not so much. You're going to have to spend a little bit of extra time using the quadratic formula for those last two irrational zeros. So please check that out. See if you can get that to play out in that manner. I wanted to finish up here with the polynomial inequalities. It kind of takes us back to the very beginning of the lesson. The boundary algorithm, a sign chart, or graph will be our analysis and our approach. So looking at this original quadratic inequality, we can see here that it is a quadratic less than 3. Your first goal, if you remember from the first page, is to set it less than 0. Okay. Note that this is a less than inequality, so because that's the case, we want negative, not positive outputs. And because it's less than, we want open circles that are critical numbers. So I rewrote the quadratic. Again, I subtracted 3, so I have this less than 0. I should highlight that again if I haven't already. Subtract 3, it's less than 0. Now we set it equal to 0 to get our two factors, so please double check how you factor. 2x plus 1 times x minus 3 is the factored version of that quadratic. Set this equal to 0, we get -1/2. Set that equal to 0, we get 3. Open circle at -1/2 on the number line. Open circle at 3 on the number line. The question then begs, what direction are you going to go into? Are you going to go left of -1/2, right of -1/2, left of 3, right of 3? Yet again, you can use your graphing calculator. You can use the sign chart. In other words, you can go ahead and use the store feature if you'd like. If we do this, for example, we know that -1 is less than -1/2. So if I were to store that as x, yet again, I can go through. And if we remember, again, using this quadratic, essentially 2x squared minus 5x minus 3. We want it to be less than 0. So let's see, 2x squared minus 5x minus 3. Okay, so there's your quadratic, and the output, because it's a positive number, 2x squared minus 5x minus 3, when you plug in -1, you get a positive output. You get positive 4. And because we wanted negative outputs, you do not graph left of -1/2. And because of the nature of how we know quadratics are going to look anyways, look at how my dashed parabola takes shape. If you were to graph this on an XY axis, you actually have a parabola that crosses at -1/2 and again at positive 3. Turns out that if you plugged in 0, not surprisingly, you get -3 less than 0, which is true. So anything in between these 2 points is going to work as a solution, while anything to the right of 3 simply will not. And you can test that again using your store feature. That's a nice quick way to do that. I would argue that the approach that I just went through is the boundary algorithm, but also in a sense, you're using the sign chart analysis, not because we care about the number per se here. We care about the sign. The sign is positive. To finish up, our final answer in interval notation, parentheses at -1/2, parentheses at 3. Please try example 2 on your own. Take a look at how it frames up. And I also advise you to take a look at the additional notes. These additional notes will help you in your assignment for tonight, which should be this worksheet, Solving Inequalities.